Clap your hands. Come on and dance. Listen to it. And take the band. Hit it. Hit it. Hit it. Hit it. Ah!
Welcome back. We're going to talk some more about some applications now. Last time we discussed the example of a block attached to a wall by a spring. We measured the displacement of the block by a single scalar valued function u of t, and we got the second order linear equation mu double prime plus ku is equal to 0. And we analyzed that, and we saw that the motion of the block is given by, it's a periodic motion. U of t is r cosine omega t plus some phase shift, where omega is the square root of k over m. Okay, and then we also discussed what happens if there's a friction term, which is a term involving u prime, so that's mu double prime plus beta u prime plus ku is equal to 0. And we're going to generalize this today and look at a vector valued version of this. So what we are going to be talking about is a setting with multiple springs and masses, possibly different spring constants and different masses. I'm going to ignore friction for the sake of this discussion. And so rather than the single scalar valued function u, we're going to have a vector valued function of time u of t. So u is u1 through un, where each ui is a scalar valued function of t. ui is ui of t. And what the picture is as I said, you have a bunch of springs connecting a bunch of masses, and out of the arrangement you get some matrix K. I'm not going to say too much about exactly how you compute this matrix, but the picture is something like this. You have a bunch of blocks, and they're all connected to each other by springs, and they're in some positions which are described, and the springs, which ones are connected by springs, are described. And out of this information you get this symmetric matrix K. I'm not going to explain the derivation of where that comes from, but I'm just going to jump ahead and say, using Newton's laws, out of this you get an equation which looks like this from F equals ma, where u is, remember, this vector valued function. You get something very similar to what we had before, which is that u double prime plus k times u is equal to 0. So it's just like the equation before with no friction, except that we've replaced u now with a vector valued function. And the analysis of it is quite similar. So just to be completely concrete, if n was equal to 2, I'd be talking about this 2 by 2 system like this, where I've brought the k to the other side, if you wish. All right. Okay, so this is a second order equation, second order because of this double prime, and it's linear. So as usual, we're going to be looking for a number of linearly independent solutions, so that the general solution is a combination of those. And let's go back and look at the case when n is equal to 1 to remind ourselves how that worked. So we have this vector equation like this, and when you set n is equal to 1, you have this equation, and I've taken m is equal to 1 here. And we saw last time that the solution it's oscillatory. It can be written as in terms of a sine or a cosine. And for example, what you get is the basic solution looks like this. Cosine radical kt and sine radical kt are two basic solutions, noting that k is greater than 0, so radical kt is a perfectly good thing to write. And so let's proceed by guesswork, which is always a good thing to do when you're talking about differential equations. You try and guess a solution and see if you can make it work. By analogy with the one variable case, let's try and guess that u of t should be some cosine of omega t times some vector, where I don't know what omega is and I don't know what the vector is, but hopefully I can pick them to make this function a solution to the equation. And the way you do this is you just make this guess and then you try it and plug it in. So if u is equal to cosine omega t v, then u prime is minus omega sine omega t v. And u double prime is, there we go, that's sine. And u double prime is minus omega squared cosine omega t v. And so you plug this in and you see that you get the equation minus omega squared cosine plus k times cosine omega t v. That's supposed to equal 0. And so you can cancel the cosine terms and you get that obviously v is supposed to be an eigenvector for k with some eigenvalue. Let's see, it turns out to be that you want minus omega squared v plus kv is equal to 0, which is to say kv is supposed to equal, there's a plus is equal to 0, which says that kv is supposed to equal omega squared v. So if we choose omega and v to make this hold, we'll have a solution to the equation. That is to say, v has to be an eigenvector of k with eigenvalue omega squared. Well, if that's going to work, you'd better have that the eigenvalues are positive so that they're of the form omega squared. Otherwise, you're going to, you know what happens. So let's suppose that all of the eigenvalues of k are greater than or equal to 0, and if you list them as lambda 1 through lambda n, then these omega i's are the square roots of these guys, and you get solutions of the form cosine omega 1 t times v1, where you take the vectors to be v1 through vn, and you can also use sine omega 1 t times v1 and so on, all the way up to cosine omega nt and sine omega nt times vn. Okay, now I'm assuming here that these v1 through vn are linearly independent. Otherwise, there's more work to do. And if that's the case, then the general solution can be written like this. It's a linear combination of these excuse me, sine and cosine terms. And as usual, we can, by clever choices of these constants and relabeling things, we can rewrite this just in terms of cosines. And, well, what does this look like? I'd like to analyze this solution, see what does it tell me. So what it is, it's a superposition of a bunch of different cosine terms with possibly different frequencies. These omega i's are very possibly different, and so it's a bunch of sine waves or cosines with different frequencies, and when you add them up, you don't get a sine or a cosine. What you get is something which is sometimes called quasi-periodic, if these omega i's are rational, related to each other by a rational number, then it's actually periodic. But in general, it's not. So, for example, suppose you just had two terms like this. You had cosine of t and cosine of omega t, where omega is some number besides 1. And when you add these, well, if omega is not rational, which is to say it's not a ratio of two integers, then this thing never repeats. It just it wiggles up and down. You can graph it on a computer and see it seems to be sort of irregular. If omega happens to be a rational number, then after a certain number of repeats, something like q cycles, then it starts to repeat again. And that's what I mean. This thing can be periodic, but typically it's not. And even if it's periodic, it's not just with a single frequency. It has a blend of several frequencies. Okay, so now in our applications, it's going to turn out that this matrix K that we're talking about is symmetric and positive definite. So that's great, because since it's positive definite, all of its eigenvalues are in fact positive, and its eigenvectors are linearly independent. In fact, they can be taken to be orthonormal. So everything I said previously will work perfectly well in this setting. So you have this n by n matrix. It's going to have n eigenvalues, all of them positive, and n eigenvectors, v1 through vn, which are can be taken to be orthonormal. Okay, so we have these cosine and sine terms times the vectors. And these omega i's are the square root of the lambda i's. And these omega i's are called the natural frequencies of the system. And what that means is that depending on your initial conditions, it might actually be just a single omega I in a very simple periodic motion. And then the general solution is a linear combination of these. And these ones with just a single omega, sines and cosines, these are called the normal modes. These are the simplest solutions to the differential equation. And so let's illustrate all of this with an example, the simplest example beyond the one, which is where you have two masses. So let's say that you have two masses and three springs attached like this. And the springs are attached to the floor and the ceiling at the ends. And you have three spring constants, C1, C2, and C3, and two masses. I'm going to assume that the masses are both the same and can just take them to be one. And in the part of the discussion that I'm skipping, there's an explanation of how to get this matrix K out of this situation. And well, I'm just going to write it down in this example. It turns out that K is given by the following expression. The matrix constants, the spring constants give you a diagonal matrix, and these gets modified like this. And what you get is K is this 2 by 2 symmetric positive definite matrix given here. Okay. So I'm going to consider this equation U double prime plus KU is equal to 0, where I'm using this K from over here. And I'm going to interpret it in terms of the this picture of these blocks attached by springs. Okay, well, let's just take a case where all the spring constants are the same. That should be the simplest. So in that case, this matrix K turns out to be this. And it's easy enough to compute that there's an eigenvalue 1 with vector 1, 1, and there's another eigenvalue 3 with eigenvector 1, minus 1. Okay, so what happens? The solution to this thing looks like the following. You get a cosine 1 times t, and sine of 1 times t, and with the corresponding vectors, and then also these cosine and sine of radical 3t. And you get these linear combinations, and as usual, I'll skip the algebra and jump to the punchline. The general solution looks like this. You get something involving a cosine t times this vector 1, 1, and then you get another involving cosine of radical 3t and a phase shift, and I apologize, this second term is missing the radical 3. So each one of them has, it's a cosine omega t with a phase shift, and there's these two eigenvectors in there, 1, 1 and 1 minus 1. And that's the general solution. Okay? And so these two terms are the normal modes, this one right here and this one here. And again, this second one is missing a square root of 3 in front of the t. Let's look at what these mean. The first normal mode is where you take R2 is equal to 0. And this 1, 1 is telling you that U1 and U2 are equal, which is to say that the two blocks are moving together. U1 and U2 are the displacement of these two blocks. And so if one of them's moving up, the other one's moving up, and then if one of them's moving down, the other one's moving down, and the distance between the two of them is fixed. And so just imagine you pulled the whole system down and let it go, and it would just bounce up and down as if there was just one block. And the second normal mode, well, in this case, these two entries here have opposite signs, what that means is the blocks are moving in opposite directions. So that basic mode is where you start by pulling the two blocks directly apart from each other and let them bounce back and forth in completely opposed motion. So one of them will be moving up while the other one's moving down, and vice versa. And that's quite a simple solution. You can just picture how that works. And those are the two normal modes. And then the general solution is a linear combination of those two. Now, a general solution is going to look extremely complicated, but the two normal modes are very simple, and what this shows is how very complicated behavior can be obtained by a combination of these two rather elementary ones.